All right. Hello, everyone. Welcome back to the Multi-Agent Learning seminar. Today, we're really excited to have the Multi-Agent RL research team from InstaDeep presenting. So it's going to be like a few of them presenting here today. The Multi-Agent RL research team at InstaDeep works on large-scale multi-agent learning with a focus on algorithmic innovation in cooperative systems for industrial application. The team regularly contributes to the research community through publications at venues such as NeurIPS and ICLR, and to the open source community by releasing open source software for MARL research. Yeah, so whenever y'all are ready, take it away.
Amazing. Thank you so much. Thanks, Rupali. And once again, thank you so much for having us. It's an absolute pleasure to be here today. My name is Ruan. I work as a research engineer for InstaDeep based out of Cape Town, and I'm currently leading our efforts for building this MARL ecosystem. We're absolutely thrilled to speak to you guys today about growing this MARL ecosystem in JAX. It'll be me and a few of my colleagues that will introduce themselves as they go along. So just to show, this is it's been an effort that's been coming over multiple years, and so just to highlight here quickly, these are the current active contributors on the InstaDeep MARL ecosystem project. But it's also had many past contributors that have been both internal to InstaDeep, but also public contributors, and then also MARL's work by a whole community. And so today it's so nice to see you guys here, Alex and Ben. I can't see if there's anyone else here as well, but shout out to like JAX-MARL and the work that they're doing as well, and then also to Chris with the work on Peer JAX-RL, and also like indirectly Clean RL even as well. We're really happy to be like part of a larger MARL community driving research together. So the first question that one could ask is why are we developing this MARL ecosystem? And it comes from the fact that we really want to solve hard multi-agent problems. Not only us at InstaDeep, I'm sure the greater MARL community as well. And in order to do this, we need to push the research frontier in MARL. And since MARL is so software development intensive, we want software that is reliable. So we have reliable baselines to start from, but also software that's flexible and easy to hack, to do new research, but also software that can really scale and leverage modern compute. You also want stable and maintained tooling, something like environment suites. And then all of this we also want to do with robust evaluation built in. And this really comes from a greater goal that we have as a team to really push for standardization in the field, so that we all as a community together drive meaningful and impactful research so that we can solve these hard problems together. So it's for this reason that over the last couple of years at InstaDeep, we've been pushing towards building this ecosystem, this whole MARL software ecosystem that plugs in to each other and is tightly coupled and works well. So to just start by highlighting here, this software ecosystem stands on 3 pillars. The first being stable and maintained software tools, which comprises tools like replay buffers or environment suites, and also tools for easy statistical aggregation of experimental results. Then the second pillar is easy starting points for research, which is these repositories with online and offline multi-agent RL algorithm implementations that's really not meant to be installed as packages, but really meant to be like forked, copy-pasted, and hacked to do novel MARL research. And then the third pillar, which is these community artifacts, which is there to benefit the greater community, which we believe will be statistically robust benchmarks and baselines and offline MARL datasets, which all together culminate in impactful and reproducible research. Just a primer, this entire ecosystem is JAX-based, like we mentioned in the beginning. So just a primer for everyone who's here. In very simplified terms, JAX is essentially NumPy code that can be compiled down and run really, really fast on modern accelerators like GPUs and TPUs. JAX follows a functional paradigm. And so I just want to mention sort of 3 function transforms that we're going to speak about quite a bit in this presentation. The first one being JIT, or just-in-time compilation, which essentially, given some function X, this function can be just-in-time compiled so that it runs really, really fast on these accelerators. The second transformation being VMAP, where essentially, given some function f that operates on some single input x, if we transform it with VMAP, that function is automatically vectorized, and so it can operate over a batch of inputs, or like a vectorized set of inputs, and produce vectorized outputs. And then extending VMAP, essentially there's PMAP, which is just auto-parallelization. It essentially, you can think of, given this function f that operates on x, we can transform it with PMAP, and then we can run like a batch of runs over multiple devices. So just to go back to show these 3 ecosystem pillars, and now we'll sort of dive in one by one into each of these pillars.
Awesome. Thanks, Ron. Hey, everyone. I'm Sasha. I'm a research engineer at InstaDeep, and I mostly work on Maava and Jumanji. So yeah, to dive into like the first of our software tools, being Jumanji, that is a native JAX environment suite for reinforcement learning, which is specifically focused on industry-inspired problems. It comprises both single agent and multi-agent algorithms, but for this talk, I'll just be focusing on the multi-agent part. And so you might be asking yourself, why do we care about JAX-based environments? What's so important about that? Well, the big thing is that if you've got a JAX-based environment, you can compile it down, run it on your accelerator as well as your algorithm, and you firstly remove the bottleneck of CPU to GPU communication or CPU to TPU communication. But you can also run multiple copies of this environment because generally accelerators are pretty good at parallelization. So yeah, just to take a bit of a deep dive into a very quick code example for Jumanji. It's super easy to install. It's pip installable. It's a very familiar DMN API. It's got make. It returns time steps. So if you've ever worked with any DMN style environments, that's how it works. As a kind of feature of being a JAX-based environment, it's got really nice reproducible rollouts. So every JAX random call is seeded, and so if you start with the same key and you take the same actions, you'll get the same reward every time, which is obviously super useful for reproducing results. You can render your environments. Got a nice gift there. And yeah, as Ron mentioned earlier, because again this is a JAX-based framework, it adheres to JAX's kind of rules. You can both JIT and PMAP your environment step and reset functions, which of course gives you a massive speed up. Cool. So just to chat about kind of what multi-agent environments are available in Jumanji. So firstly, we decided that it would be really useful to reproduce some existing multi-agent environments that already exist in the literature, and so we decided to re-implement robot warehouse and level-based foraging from the Edinburgh group. And so of course we see quite a nice speed up over there, NumPy or Torch implementations. But we also made a whole lot of new multi-agent environments. So just to quickly take you through these, there's Cleaner, which is basically you've got a whole lot of agents that need to clean a grid together and clean it as fast as possible. You've got Connector, where you have agents that need to connect to their kind of desired goals but not block each other. And then you have multi-capacitor vehicle routing, which is basically multi-agent traveling salesman problem. Cool. So that's kind of a quick overview of Jumanji, and how it fits into this ecosystem is that it's firstly Maava's base API, and secondly it provides us with fully JITable training environments. That being said, it's not the only thing that we use in this ecosystem. Like, we're totally open to and do currently use other environment suites such as JAX-MARL and GigaStep. Yeah, so next on the list is Maava. So Maava is our collection of algorithms, really. And so a core tenet that we kind of use when developing this library is that we want it to be hackable and scalable. And so a very important thing that we don't really want is for you to be able to pip install this library. You could, but that's not really its intended use case. The intended use case is for you to fork it, for you to clone it, download it, hack away at it, take PPO and do something crazy with it. But you'd have this really great starting point where you've got scalability built in, logging built in, evaluation built in, but it's all available to you in a single file and super hackable. Yeah, so to kind of dive deeper onto the scalability aspect, we use the Anakin architecture for kind of our scalability, and we can do this because we require JAX-based environments, so we can put the environments and the algorithms on the accelerator, and get a huge amount of speed up from that. To like kind of zoom in on this picture, we can initially like vmap the end step function, and so this is kind of akin to the Jim multi-process wrapper. If you've ever used that, you can get a whole lot of copies of your environments and then get a whole lot of experience from that. But we can take it a step further, where you can actually vmap your act learn loop, right, and do a whole lot of those vmapped end steps, do that multiple times, as well as learning multiple times. And we can take it a step even further and pmap this whole thing. So you run it across multiple devices, and basically what this ends up giving you is just effectively massive batch sizes and a huge amount of data to train with. And that, of course, speeds up learning. Right, so to zoom out again, I showed you the top part of the graph. Now the bottom part of the graph is basically just what we do with the gradients. We mean over those, vmapped and pmapped learn steps and produce a new set of parameters and start the whole process again. Yeah, so just to show you what Maava directly has on offer, we've got a variety of algorithms, so PPOs, the soft critic family, Q-learning all the way to Q-mix, and recurrent and feed forward and centralized and decentralized versions where they apply. We also support a whole bunch of JAX environments, all with a huge amount of scenarios from Jumanji, JAX-MARL, GigaStep, and of course it's very easy as long as you conform to the Jumanji API, which is pretty easy with a wrapper, and we have some examples of how to do this. You can support your own environment very easily. Yeah, we pride ourselves in trying to maintain a research-friendly code base. So really a single file implementation with the core algorithm logic, being as short and concise and readable and understandable as possible. And then finally, very reliable. So we've got integrated evaluation. So if you run any of the systems, they can produce reliable plots. And we also provide a whole bunch of nice general and multi-agent RL specific utilities, such as networks, checkpointing, logging, and the like. So I told you that it was pretty performant, but we need to come with some receipts here. So if you look at the top graph, that's comparing Maava's performance to the baselines reported with SMAPs. And as you can see, Maava is matching or outperforming the baselines provided with that environment suite. And then in the bottom one is more comparing to the non-JAX versions of the algorithms. So, of the environment. So we've got LBF here, and the blue line is the non-JAX version, and then the green and orange lines are the JAX version. And so of course those are run on accelerators, and as you can see, it's just warp-up time is just way faster. Cool. So that's Maava, and how it fits into the ecosystem is really it uses Jumanji's API. We're able to produce reliable experiment data, and eventually use it to produce our own research, and that's really a key about Maava, is that it's an evolving tool, really. We use it in our own research, and so the best practices and things we like and don't like about Maava are always changing. As we find things that we like and we don't like, we modify them. Yeah, so that's Maava. I'm going to hand over to Calvin.
Hello, everyone. My name is Callum, and I am a junior research engineer at InstaDeep. And I'm going to chat briefly about flashbacks. And essentially, you might be wondering, well, okay, we have Maava, we have Jumanji, and it's fantastic that everything can exist in this jittered context. But what about off-policy algorithms? What if we have some sort of data that we want to use in our algorithms? And you can imagine the difficulty there is that we are generating data, but how do we kind of keep it in this jittered context if we use a traditional replay buffer structure? And so this need arose where we found that, I don't know if maybe Sasha, do you want to chat about this Maava question now, before we head on to flashbacks?
Sure. Let me just read it. Sure. So for question one, totally. There's no like strict plans, but we totally are investigating just larger models in general. And so this is certainly something that will be looked at in the near future. And then in terms of performance on GPU and TPU, this is actually a really interesting one. It's very highly dependent on the environment, and we found that certain environments actually don't run super well on TPUs. There's some weirdness with how XLA compiles down to certain operations that just seem to not work super well on TPU. So mostly, as a rule of thumb, TPUs are better or faster rather. But certain environments we've seen very bad speed on TPUs.
Also, to just jump in on that, on the performance differences, there's certainly, like Sasha mentioned, a difference in speed, but as far as algorithmic performance, we find them to be essentially the same. The only thing to be mindful of when using TPUs out of the gate is that TPUs tend to have quite a few more cores, and so effectively the batch size is increasing quite a bit. So one just has to be mindful of this when you want to compare, for example, between a single GPU device or a TPU with 8 cores or something like this. You either just have to scale down the number of environments per core or just adjust other hyperparameters accordingly. But for the most part, the performance is matchable between the two.
Cool. Yeah, thanks. Thanks for the question, Alexander, and thanks for the answer, guys. So we were talking about flashbacks, and essentially the need arose out of wanting to create off-policy algorithms while still remaining in this jittered context, right? Because we want things to be fast. We want, much like Jumanji, we want everything to kind of live on the accelerator. And there were people doing this, but we wanted a really well-engineered, streamlined library that was really good for the purposes we had in mind. So we created flashbacks, and flashbacks is essentially these accelerated replay buffers written in JAX. And just to kind of highlight some of the key features, it's also pip installable.
Callum, I think we lost your voice. Still can't hear you.
Interjection. I think his headphones battery just died. He's going to just share quickly now.
Can you hear me now? Is that better? Yeah. Fantastic. Sorry.
Yes,
Sorry about that. So yeah, I was looking at flashbacks being pip installable, and it was very intentionally designed to be a lightweight library with essentially all the necessary features that we have in mind, with minimal bloat, and ensuring that it's super quick and super reliable. And the important thing about these buffers is that it's purely functional, which is perhaps slightly different to what you're expecting in a typical replay buffer library, because you kind of have this natural state, these like objects of your buffers. But we have these pure functions. So you can see there the buffer function is actually just a pure function, which then comes with an initialization function and an add function, right? And the benefit of that, even though it might look a little bit strange at first, is that we can now JIT things like adding to the buffer and sampling from the buffer. So here we see that there's an add function, buffer.add, which we can actually compile now. We give it the state, the old state of the buffer, and we give it a new time step, and then we receive a new state, right? And that is all compiled, which makes it super, super fast. And it also has efficient memory management. And so there's some nice JAX primitives there of donating memory. So it's making sure you're not duplicating that amount of the state memory that's getting allocated. So that makes it super fast. And then the sampling is also jitterable. And you'll see there's also a random key there. And as Sasha mentioned, for seeding the Jumanji environments, we also have this deterministic pseudo-randomness, which is very, very useful. Yeah, so that's Flashbacks, and we use it in a lot of our projects, and it's really fast and really nice to use. But the next kind of thing is a utility within Flashbacks is that, say we have these buffers now, and we want to store that data. An obvious use case is for offline reinforcement learning, but you can imagine all sorts of other use cases in just terms of checkpointing your buffers. Perhaps you just have a long run that you, in case it crashes at some point, you want to checkpoint it. And so that's what we created Vault. And Vault is a utility that lives within Flashbacks. So it's a very lightweight utility, single file that lives within Flashbacks. And it essentially just wraps an experience structure. You give it some sort of structure of your data from a Flashbacks buffer. And then periodically, it's as simple as writing the Flashbacks buffer state. So you see on the left, we have this state object. Every now and then, you exit your jittered context, because obviously you now are writing to disk. So you train maybe for however many steps, you exit that jittered context, and periodically you just write that to disk. And Vault will handle all that bookkeeping for you. So it's very, very simple. But what's nice is that there's this tight integration that at a later stage, perhaps in a different context, you actually just read from that Vault and you use the data in the exact same way as before. So we still use those same pure buffer functions. You can see that that loaded state is in the exact same form as a normal Flashbacks buffer state. And so there's that native integration, which works really, really well, and particularly for what we're going to be speaking about next, which is offline RL. And so just to kind of show how it's fitting into the ecosystem, Flashbacks enables off-policy algorithms in Maava, and our off-policy algorithms do use Flashbacks, and it remains very, very fast, which is great. And we also have this utility to record data to disk, which is Vault there. And you can see that Vault is comprises multiple Flashbacks buffers, and this is how we record data. And that's a nice segue into chatting about offline RL, which Claude will be chatting. The question, did I understand? So the question is, does the replay buffer allocate the whole buffer right away and then expand when changing the state? That is not the case, because kind of upfront, JAX wants your array sizes to be constant. And so upfront, when you're creating the buffer, say you want 1 million time steps, it has to allocate that in memory, right? And that state that you're passing around, because you're passing those million elements into the, suppose, like, the buffer.add function, and then getting the new state out, we need to keep those shapes consistent. But what's nice about the utility of Vault is that Vault only takes up the amount of space on disk that is required. And so you can make a smaller replay buffer that can fit on your accelerator, such that every now and then you can exit that context, write to disk, and that can then be any sort of arbitrary size. And so that flexibility is kind of the necessary trade-off for still allowing that speed in the jittered context, while having essentially an unlimited storage size through Vault. I trust that answers the question, Alexander. Thanks for that. And then you're Polly.
Yeah, I had a quick question and a quick pointer. Yeah, like just for the recording, if you're answering a question, I guess if you could repeat like the gist of the question, that would be great. Yeah, and my quick question was, so does Flashbacks support like single agent stuff as well, or is this only for multi-agent?
Yeah, so much like Jumanji, these tools are being used throughout InstaDeep, not just within the MARL context, and not just within the MARL team. And so Flashback, certainly, it actually is very, very actively used in some single-agent RL projects. And at the end of the day, ultimately, it is actually just a mechanism to store pi trees, arbitrary pi trees in JAX. Now, there's a natural use case there with RL. But what's quite cool is to actually think of other use cases where when might we want to store pi trees of data, in that kind of way. And so we use it for RL, and we specifically, our team uses it for MARL, but it's certainly used for single agent RL. And a lot of people, I think, are enjoying that use case as well.
Awesome. Thank you.
Cool. Yeah. So I'll hand over to Claude now to chat about the offline work.
Cool. Thank you, Callum. Hi, everyone. My name's Claude. I'm a research engineer at InstaDeep and also a PhD candidate at the University of Cape Town. So I've been driving our efforts on OG-MARL, which is basically our set of offline MARL baseline algorithms and datasets. So with Maava and Flashbacks, we're able to generate a lot of MARL data. And then the question becomes, how can we most effectively use that data for our MARL experiments? Like, can we use it to jumpstart future MARL runs, or indeed just train fully offline? So offline reinforcement learning and offline MARL in this case is basically when you've beforehand collected a whole bunch of experience from a set of behavior policies. So in this diagram, the purple box, the behavior policies could be handcrafted controllers, human operators, or indeed other RL policies. And that data was collected into a large buffer or data set, and then you train on that using your RL or MARL algorithm. But unlike in online reinforcement learning, where you periodically redeploy your policies back in the environment to collect more data and add to your replay buffer, we now have this decoupled setting where you no longer can do that, and instead you can only deploy your policies right at the end when training's over, and that's the orange block there. Now, offline RL and offline MARL is a really appealing paradigm because there are many real-world settings where it might be impractical, or indeed like dangerous to collect real-world data, but we do have tons and tons of real-world data sort of collected from humans, say, doing a task. And like, if we could develop techniques to utilize that in our MARL and RL training loops, that would be amazing. Now, offline RL has developed very steadily over the last few years and had some great success, but offline MARL is a younger field that's in the last 2 years grown a lot in popularity. And when we got into the field, like, a thing we noticed immediately as a huge challenge was that everyone was generating their own data sets whenever they did their research project, had different APIs, and importantly, didn't shed much light on the process on how they got their data sets and what the experience in the data set is sort of comprised of. So we did a sort of baselines paper where we generated a whole bunch of data sets on all these very popular MARL environments, including SNAC, multi-agent Mujoku, Flatland, Petting Zoo, MPE, and a few others. And then really did a lot of work to profile the data sets and give a lot of qualitative and quantitative information about the data sets, because as it turns out, the performance of your offline RL algorithm depends a lot on what the data set looks like. And yeah, we made that sort of available to the community and hope that it can be used as a standard benchmark for offline MARL. But we also released the utilities that we use to make the data sets. So, for example, an experience recorder, which you can use to wrap an environment and then collect data from your online RL MARL policies, interacting with the environment to then use like downstream and offline MARL. So to illustrate here, like, you'd wrap your popular robot warehouse in our wrapper, and then it'll intercept the interactions, the observations, actions, and rewards, and then sort of just send them to a vault, which is then stored on the disk, and you can reload that data in later. And then we try to make it as easy as possible for people to run our baselines on the combination of different data sets, environments, and scenarios. So there's really many configurations for which you can run these things, because for every scenario we generated poor data sets, good data sets, and then mixed data sets as well. So yeah, the original implementation of OG-MARL was in TensorFlow, but we've now been porting everything over to JAX and are still in the process of doing that and really reaping the speed benefits of that. So yeah, to just put OGMARL into the greater ecosystem, we're constantly working on a tighter coupling between Maava and OGMARL, like I alluded to in the beginning. The idea of jump-starting our MARL algorithms with lots of offline data is a very appealing research direction. And OGMARL has let us release a whole bunch of open source data sets on popular MARL algorithms to the community, which we hope will drive research in the field. I will now hand over to our next speaker, Maima.
Thank you, Claude. Hi, everyone. My name is Umayma Mahjoub. I'm based in the Tunis office. I've been working for 2 years with the company on evaluation in multi-agent RL and Maava repository. So now that we have Maava and OGMARL, both of them have like a variety of algorithms within them, we can think about making benchmarking using these frameworks. And to do benchmarking, you need to train like variety of algorithms. Each of them should be tested in different scenarios within different environments. And of course, to figure out the stability of your algorithm in a specific scenario, you need to make like multiple seeds or multiple runs to do so. So you will end up having a huge raw experiments data that comes like from the episode returns that you gathered from the evaluation phase within each experience. So the question here is like how we can aggregate all these experiments results to make like the analysis and plots to compare between the different algorithms that you have and be like confidently fairly comparing between each of these algorithms. And here where MARL eval does live. So MARL eval is a result from a research paper that we made at NeurIPS 2022, where we focus on making standardized evaluation protocols while focusing on statistical robust analysis. So MARL eval is like also made on top of reliable from the deep RL at the edge of statistical precipice. So what exactly MARL eval do is that it get your raw experiments data and try to make automatically like different plots. Like for example, you can have the aggregated score plots, you can have the sample efficiency curve, the performance profiling, the probability of improvement, and these analysis happening on top of your different experiments from different scenarios and different seeds. And again, this is something we wanted to be as standardized as possible. So your raw data should be standardized in the following format, where the data from whenever you run an experiment, it should be recorded as the following, where you have the environment name followed by the task that you're running into it, and what is like the algorithm that you're running at that point, plus like what is like the seed or the different runs that you have. And inside of it, you will have the raw experiments returns from the evaluation steps. However, I know this could be like tricky to make it like manually or like to try to make a function for this. So what we do is something similar to benchmark, is to make like a JSON logger tool inside MARL eval that you can import it directly in your repository. And with small tweaks to your framework, for example, here Maava, we can like import JSON logger into Maava, make some changes. And once we run any experiments from Maava, the recording of the different episode reward will be in a JSON file similar to the format that we wanted. And now that you have the JSON format that you need for MARL eval, the next step is you can choose whatever like the plot that you want to do. For example, here the aggregated score and probability of improvement, and you can just call these method and it will make like these plots. For example, the probability of improvement, which is like the down plot, it showcases like how probably that algorithm X outperforming algorithm Y using the data that it gathered from the different scenarios and environments from the experiments that you trained on your framework. And by that, we finish up like the full ecosystem where we have Maava and OGMARL. Whenever you train them, you will have like the JSON logger within them. So the data will be adapted to MARL eval, and eventually MARL eval will make the rigorous plots. So we have a question in the call. Let me check it. So is there a documentation pipeline tutorial how to create an offline dataset for my favorite environment, and should one be compatible like with Jumanji app? Okay, no worries. So, well, the documentation, we try to make the documentation as possible. Oh, this is like for the offline dataset, I think. Maybe, Claude, this question is related for you. Yeah.
Yeah, so in this case, the OG MARL like environment API at this stage isn't even using Jumanji. It's very similar to like Petting Zoo. And you should be able to repurpose the like experience logger we provide there to do exactly what you want. And like if you need help with that, like we really encourage you to just make an issue on GitHub, and then I will be available there to help you with that. I would be very happy to do that. But yeah, it should hopefully be quite simple to understand. And there are tutorials on the OG MARL GitHub page. Yeah.
I just want to add to that. So, I mean, the OG MARL tools for Experience Recorder work really, really nicely, and it's really coupled quite well. But if you don't want to go down that route, what is also quite nice is just by using Flashbacks, you also get this ability to do it quite easily, where if you are using Flashbacks as your replay buffer thing, then and regularly writing to a vault, then that is an offline data set. And so the Experience Recorder adds all sorts of nice, very, very neat wrapping functionality. But if you wanted a quick and dirty solution, then just by using Flashbacks buffers as your replay buffer core, then creating an offline data set should be trivial.
In fact, to also add here, there's an example on Maava's repo where we do exactly that. So if you go to the Maava repo, we have an advanced usage folder. Inside there, we have a little README that explains what we're doing, but essentially we're doing exactly this with Maava. We're not even wrapping environments or doing anything. We're just using Flashbacks out the box and Vault to checkpoint experience and then train offline algorithms on this again. Cool.
Yeah, I have it to everyone now. Thank
Yeah.
you.
Awesome. Thanks so much for the question, Alexander, and thanks a lot, Umaima. It leads to the sort of final community artifact, which we haven't highlighted just yet, but it's really our belief that this ecosystem together empowers us and the broader community to produce impactful and reproducible research. So just in summary, what these three pillars exactly are is stable and maintained software tools, which comprise of Jumanji, Flashbacks, Vault, and MARL Eval. Then these really hackable starting points with algorithms that can be sort of relied upon, that they're stable, but also that they're like hackable and scalable enough to do interesting research with. And then the final pillar being these community artifacts, which is these like benchmarks, baselines, data sets, and research. In summary, here is the entire MARL software ecosystem that we're busy building. But we don't just want to leave you with that picture. We just want to demonstrate how this ecosystem can be used together. And our belief is that this in itself opens up interesting new research questions. So for example, you could start with a Jumanji environment. You can train a Maava online MARL algorithm in a Jumanji environment and store all of this data in a Flashbacks vault, which you can then load into OG MARL to do offline training. And then all of this can be evaluated and logged in a robust way. And we really believe that this opens up very interesting research avenues for people to explore. And to just mention here, the goal is really not for us to say, oh, we could train a really small scale system in a couple of minutes on a laptop, but we really want to make a call to the community and mention like what could we do if we were training really large scale systems of hundreds of agents perhaps, or we were storing data sets that had loads of different environments or even loads of different tasks. What are the sort of generalizable offline algorithms that we could train with all of this data we generate? So yeah, thank you so much for listening to us. We'd love to open up for any questions. But yeah, thanks.
Awesome. Well, I think that was a great presentation and very, very clear. I'll definitely be recommending it to a few people. Yeah, so like, once again, thank you to the speakers. If anybody has any questions, I guess feel free to like raise your hand or something. We don't need to ask them in the chat anymore. William, you want to go?
Thank you. You are focusing on probably cooperative environments with much more agents than just like two. Have you been thinking about more competitive, fewer player kind of games environment, and what would be the relation to things like OpenSpiel and so on?
At the moment, because at the core of our research is industry-driven applications, which at least for the problems that we care about, these are cooperative in nature. So at the moment, we don't have any immediate plans to extend Maava to the competitive case, but it should definitely be possible. I am probably biased because we use these tools quite a lot, but I do think it can be extended to the competitive case. We just don't have any immediate plans to do so.
Thank you.
I see there's a question in the chat from Barna. Thank you for the presentation. Could you please give some examples of applications you applied this ecosystem on? Yeah, for sure. At the moment, research. Behind the scenes, of course, we can't let the cat out of the bag with what we're working on at the moment. But yeah, the main applications have been researched up until this point. And yeah, hopefully later in the year, there will be a bunch of nice papers that use exactly this ecosystem.
Cool. I guess like that's all we have for the questions. Callum, you want to add something?
Yeah, just one thing I wanted to add. This final slide, you can see it just has all the links to our GitHub repos, and something we just want to reiterate is that we are building this stuff in the open, and it's a very, very big part of the philosophy that we have for this ecosystem, is that we don't want to just build this alone in some sort of silo. The idea is for the community to get involved, and what's really nice is that each of these projects that you see there has people working on it full time to answer your questions, to fix bugs, to make sure that we are hearing what people want, you know. And of course, we have our own use cases and we use these tools daily, but we're definitely open to engaging with the community, and we really are trying to be as responsive as possible on the repos. So please do get involved. You know, if there's a feature that doesn't exist yet, open it. Like, let's have the conversation, and you know, give us a star on GitHub, and yeah, be part of this conversation, because it's really something that we want to do in the open with the community. You know. Yeah, William.
So maybe one more question. What is the most complex environment that you have run this with? Like, where can it scale with really complex simulations, for example?
At the moment, actively testing the largest scale, like the largest number of agents we've run on at the moment, like close to 30, like the largest environment that's like natively supported in the SMAX benchmark. But we're actually busy scaling up quite massively behind the scenes, so more coming on this soon. Some of these Jumanji environments are really nice and flexible, that you can sort of scale them up and down as much as you like. So connector, for example, could be scaled to, you know, hundreds or thousands of agents if you wanted to.
I was maybe thinking more about complexity on the environment, like not just many agents, but like medium number of agents, but actual complex simulation running to understand what's happening. Like, is there any support in that direction or not?
Just so that I can understand, do you mean simulations outside of these JAX-based environments that we just mentioned?
Like, you would probably have to implement it. Like, if you imagine really something like a strategy game or something, like really complex, quite expensive to simulate. So would you have to port it to run in JAX on the accelerator, or like what would you have to do to support something like that?
With what's available right now, that is certainly a limitation, in that we only support JAX-based environments, but this is actually on the roadmap to include non-JAX environments. And also, yeah, it's on the roadmap to include non-JAX environments, where then if you have a very complex simulator, you could essentially map that to some API and then plug this in and still really leverage this like large scale compute. We just focused on the Anakin architecture, some of these like DeepMind reinforcement learning at scale training architectures. The one that we're adopted at the moment is Anakin, where you need a JAX-based environment, but essentially there's a modification to this architecture, which is called Sabalba, where essentially Sabalba is where you have exactly this. You have some environment that's not written in JAX, and so where you can still leverage distributed compute while running these environments on like CPUs at a large scale. If you're interested in this, InstaDeep has an open source repo just called Sabalba. If you go to our GitHub, we have a repo that does exactly this, where people took a really complex simulator in the single agent case, but this can definitely be done in the multi-agent case as well. And this is 100% on our roadmap for this year.
Great, thanks.
Of course, thanks for the question.
Awesome. So with that, I think we can thank the speakers again, and we can stop the recording. And then, yeah.